All right, so we left off in our 4.2 lesson. We talked all about arc length, which was a really easy formula, but then we had those fun linear velocity and angular velocity questions, which we'll see more of today when we get to the practice section. But there's one more formula we got to discuss. It's a pretty basic one. It's just area of a sector. So the area of a sector formula is given to you, and it's on your salmon-colored formula sheet as well. But it's 1/2 times r squared times theta. So the catch to using these easy formulas is that your formula is assuming that you're always measuring theta in radians. So you either have to actively convert it to radians or at least consider that when you go to set up your work. So area of a sector questions. This one's kind of strange. Jaden is really into gardening and is doing a PreCalc problem to figure out how many seeds to buy. Go her. So we have this circle that's broken up into different sectors, and the radius of the garden is 10 feet. What area does she want to use for tomatoes? So tomatoes, I believe, are just right here. So that's a 50-degree segment or sector. However, we remember that we can't use 50 degrees, so we'll get to that in a second. So the area formula is 1/2 times radius squared, so times 10 squared. And then right here, instead of putting 50 degrees into my formula, you either have to off to the side convert it, or because your next step is going to be to grab your calculator, what I'm going to do is I'm just going to write it as a nasty fraction, because who cares? So we're going to multiply it by what to convert to radians, technically? Pi over 180. So 50 degrees is like 50 pi over 180. I don't need to simplify that because, like I said, your next step is to type. So your calculator doesn't care if you simplify. So start typing, please. And of course, a decimal answer works great for me. I don't think these real-life questions, giving answers in terms of pi, makes any sort of sense. Like, you're not going to run around saying the answer is, like, 10 pi. That's weird. So I got 43.6, which we do need to be careful about labeling. This was measured in feet, but it's area, right? So it's feet squared. Are we not good? She's got that look to her that I'm not good. What did I screw up? I probably did. Did I screw up? Okay. All right, so this next question is about wildflowers, and of course I made a mistake in my key the first time, but we caught it. I didn't realize there was 2 sections of wildflowers. And they're equivalent sectors because of the vertical angles theorem here. So this is 80 degrees, this is another 80 degrees, so you're looking at a 160-degree sector there, technically. So back to our formula. 1/2. The radius is still 10, but this time 160 degrees converted to radians would be 160 pi over 180. Typing away on our calculator, and we get, is it about 139.6? I hope. Otherwise, first hour lied to me. They wouldn't, would they? Yeah? Ish? Okay. So this last question, this is a good test prep question, a good SAT question. If you have 6 ounces of wildflower seeds, you can cover 10 square feet. So she's got to figure out how many ounces of seeds she needs to buy. So it doesn't really tell you how to set this up, but anytime you have this like analogy feeling question in math, it means you need to set up a proportion. So 6 ounces of seeds will cover 10 square feet. I just write the label down because I have to make sure my proportion's set up properly. So for our wildflowers, we're trying to cover 139.6 square feet. I'm okay with you just rounding to 140 here in our math because this is real life, so when you go to do your calculation, you're probably going to buy more anyway, so who cares? So cross, multiply, and divide. And I think I'm getting like 84-ish, aren't you? Does it round to 84? Am I totally making that up? Okay. So we'll say about 84 ounces of seeds. All right, so moving along, wind turbine question. This is a very comparable question to what you're going to see on your test. This is the good kind of question that we definitely want to be comfortable with. So we said yesterday, when we have these questions where they ask you about angular and linear speed, there's kind of a set process that I want you guys to stick to. Your first step is going to be to calculate your angular velocity. And then the key in this step is to catch all your labels that you need to change. So any dimensional analysis that has to happen, I think should happen right here. So basically I'm going to write a little note to myself to watch the labels. And then once you have your angular velocity, then you're going to find your linear velocity. And this is that weird one that has a bunch of formulas. So the easiest formula to use, in my opinion, is to use that radius times angular velocity formula. So all the hard work happens on step 1, and then the second step is really easy. So let's do that. If I read through my clues, there is a clue hidden in this problem that is kind of angular velocity, but it's not quite right. It's this guy right here. So step 1, we're going to start with 28.5 revolutions per minute. And then this is where you have to read really carefully. Now on your test, Mrs. Hoffbauer and I were very nice to you. And we like bolded things that you had to watch out for. Like if I switched the label at the last minute, I put it in, or she actually put it in bold, so it was really nice. I noticed nothing here gets changed. It doesn't say like, I want your time measured in seconds or hours. So you get to keep your time label whatever you want. The problem though is we know omega, the theta value has to be measured in radians, and you're not currently measuring in radians per minute. So you do need to convert this to radians per minute. So revolutions needs to cancel out. Tell me an equivalent amount of radians that's equivalent to 1 revolution. 2 pi radians. Very good. So omega, angular velocity is, I like decimal answers for this, so 28.5 times 2 pi is it about 179.1? Okay, so the label here right now is radians per minute because the revolutions are gone. This is angular velocity. That's only step 1 though. So when it says angular speed, there you go, angular speed. Step 2, find linear velocity by taking radius times angular velocity. So there's a radius somewhere in this problem. Do you see it? Yeah, the length of the blade that measures from the center out. So the radius is 27.1. And then underneath it, I'm just going to write a little note to myself that that's measured in meters. And you're going to multiply it by your angular velocity, which we just found, 179.1. And that was measuring, remember, radians per minute. And this is where sometimes kids get a little confused because they're like, what's going on with the radians? Like they just mystically disappear. It has to do with the fact that there's a revolution incorporated into your formula, so just don't worry about it. Yes, you can think of the radians as disappearing, but what's happening here is you get a decimal, of course. What is this? 4852.8. Why am I switching colors so much? 4852.8. The label, if you ignore the radians, is meters per minute. So, if for some reason I came back at you with this problem and I said, oh, never mind, I need my, is that not the right number? You have a weird looking face. Oh. What did I do? Oh, the decimal part? Who knows what I did? Oh, did you truncate this to 179.1 or did you keep the full decimal? Maybe I didn't truncate at some point. I don't know what I did. All right, anyways, we're thinking this is 4853.6. We'll go with it. All right, so meters per minute is the label. If at some point, like say on your summative next week, you notice at the end of the problem it says, I want your answer in meters per second, your work wouldn't be done if this is where you stopped. You'd have to go back and convert. But that's why we're going to see a problem coming up soon where I have you convert the labels right at the beginning of the problem. I think it works out nicer. All right, centrifuge. Those gross things that separate your blood cells and stuff. Yuck. All right, so this guy is, this is kind of weird. So they went ahead and flat out gave you angular velocity in the appropriate, like, notation. That's angular velocity in radians per second. So I think we're going to actually come back to that clue and use that clue later on in the problem. But let's talk about converting this to rotations per, or revolutions per minute. So you're going to take your given, which is 400 pi. I don't know what just happened. 400 pi radians per second. And they want revolutions per minute. So you're going to have to convert the radians to revolutions, which is weird. But in real life, that makes more sense, right? You would rather know how many revolutions something's doing than how many radians it's doing. So revolutions, and then you got to convert seconds to minutes. So we got two things to analyze. All right, let's start with how do you whoops, how do you convert from radians to revolutions? So that fraction says that there's 1 revolution is 2 pi radians. You just got to be careful where you're putting them. So let's put 2 pi radians down here. 1 revolution up here. And then obviously you can go from seconds to minutes if you remember that there's 60 seconds in 1 minute. So I want 60 seconds up top here. 1 minute on the bottom. I can cancel then. And this is kind of like my favorite part of the question, is cancel all these, so I'm going to always do that. All right, on your calculator, please, could you type 400 pi times 60, and then divide it by 2 pi. If you're using that exact typing in your calculator, make sure you put parentheses around the numerator and the denominator, but can you guys tell that the pi's are just going to cancel? So don't overthink it. You should get 12,000 RPMs, which is more of a real-world answer. Unfortunately, part B, they want me to find the linear speed, which I'm just going to go back to my favorite formula, r times angular velocity. So the radius of this centrifuge is 8 centimeters. The angular velocity, remember, it has, in order to use this formula, it has to be the radians per time. So I'm going to go back and use this guy. So my labels here, let's see, this is centimeters, and this one, remember, was measured in radians per second. So when I go to provide this answer, which is pretty large, it's 10,053.1. How'd I do on that one? Is that the right number? Who knows? Who knows what the brews out today? The label, remember, radians is not going to be considered. You have centimeters per second. So if for some reason, whoever I'm doing this calculation for says, no, I need it in centimeters per minute or something, I got to go back and calculate a little more. But they didn't say, so we're going to go with it. All right, this next problem is a mystery to me, because I don't know what any of these things mean. So a flywheel is mounted to an engine crankshaft. Are those even things? Is this one? Okay. Just checking. Sometimes I read problems and I'm like, this is just some gibberish someone wrote down. Okay, those are things. Good deal. Like in a car engine? That kind of engine? Is that what it is? Okay, cool. See, you learned something new. Anywho, it's got a radius of 6 inches. The engine is running at 2,800 RPMs. So this is the clue that is like kind of like angular velocity, but we're going to have to do a little work on it. So I'm going to write sort of angular velocity. So this is the 2-step process. You're going to first start by fixing up angular velocity, and we're going to fix labels at that step as well. And then second step is to go find linear velocity. So step 1. Right now I have 2,800 revolutions or rotations, either one, per minute. And then I kind of look ahead in the question. Obviously I need to convert revolutions to radians. So I'll go ahead and throw that down. But I think there's one more thing we need to take care of. If you look ahead in the question, it wants your final answer that we're going to get on part 2 in feet per second. So you also need to convert minutes to seconds. So 1 minute is 60 seconds. All right, on your calculator, 2,800 times 2 pi divided by 60. I think you get 293.2. radians per second. So that was angular velocity in radians per second. They want linear velocity. Read carefully, because it almost tripped me up first hour. Feet and inches. All right, so it says, we know this next step is easy. It's just r times angular velocity. However, the radius is 6 inches. The question says feet per second. So you can't tell me the radius is 6 inches. You got to tell me the radius is either a half of a foot or 0.5 foot or 6/12, whatever you want to do. So that's the radius, now measured in feet. And then angular velocity was 293.2, and that's radians per second. We don't worry about the radians thing. So right now you have feet per second as a label. I just need you to do a little calculation for me. So, I got 146.6. And then we just decided that was feet per second. So that was a really good question to kind of be worried about labels, because that's what shows up on your test, where you do have to watch your label. At the very end of the problem, though, it's going to be in gigantic bold letters. You know, the label has changed, so make sure you've effectively changed it properly. And I know there's some homework problems coming up where you got to do that too. All right. Everybody's favorite. Flip over and put your formula sheet away. Oh boy. I love the unit circle, don't you? What? That wasn't the right answer. It's not that bad. It's not that good either. But it's something your calc teacher wants you to know, right? I'm going to blame calc. Alright, so there's not like a right or wrong way how to fill out the unit circle, but just for full transparency's sake, when you guys show up on Friday, we got other stuff to do Friday. But at the end of class, I'm going to give you exactly 10 minutes, no more, to fill out the unit circle without any aid. So you can't use any calculators of any sort, and obviously no formula sheet. So your approach to how you fill out the unit circle, I mean, it's different for every person. And it also depends on how you're filling it out. Like if you are straight up memorizing part of it, because you're like, no matter how I teach this to some kids, they're like, I'm never going to remember how to get it, but I can memorize 6 things really fast. Well, if that's your approach, if you're memorizing something, then you need to hurry up and fill that part out really quickly on the unit circle as soon as you get it. So, in my personal opinion, the part that kids struggle with the most is filling out the radian measure in terms of pi fractions. That's the part everyone hates. So, when I developed the unit circle, because I'm a terrible memorizer, I fill out like the angles first, because that I know. And then I fill out the radian measure next. And then I completely fill out, well, the quadrancials, because those are easy. I fill out the first quadrant all the way, and I use 3 different colors. And then I take each family from the first quadrant, and I finish them up, one at a time. Okay? With me blabbing, it's going to take me like 10 minutes. And that's with me blabbing. You doing it independently has to take under 10 minutes, okay? Here we go. And on Google Classroom, I put an assignment that says, like, practice developing the unit circle. I attached a blank version of this, like, as a PDF, so you could print out extra copies of it if you want. And I also attached an older video from last year that's just me going over this. I'll be honest, every single time I teach this lesson, I've done it differently. So there's no right way, guys. Sometimes I start with the radians. I don't know, I'm crazy like that. All right, so I'm going to do degrees first. Feels good. 0 degrees. All right, what's this first one? 30 degrees. And then it is, drawn to scale. So remember, it's not quite a 30-degree jump anymore. Now it's a 15-degree jump, right? So 45 degrees, and then 60 degrees, and 90 degrees. What's this next one? 120. And then 15 more is 135. 15 more is 150. And then a bigger jump all the way down to 180. And then a 30-degree more jump is 210. 225, thank you. 240. 270. 300. 315. 330. And then you should get back to 360. So, that should be nice and easy for you. This is the part that I get nervous about, just because I know some of you guys don't enjoy the fractions. So, you have to get yourself going. I suggest, if this is where you think you're going to struggle, you fill out what are called the quadrancials, the axes. So 0 is 0 radians. That's easy. Do you guys remember what's up here? Yeah, it's half pi, pi over 2. So this is 1 pi. So if you want to count by half pies, you can. This is 1/2 pi, 2/2 pi, so this must be 3/2 pi. And then back to the beginning would be 4/2 pi, which is 2 pi. Yeah. Okay. All right. And then it gets kind of exciting. So if you're nervous about this part, do this carefully. 45s. are probably my next favorite family. Do you remember what radian measures equivalent to 45 degrees? Well, don't think too hard. If this is pi over 2, and this is halfway to that, that must be pi over 4. So what I'm going to do now, and by the way, this is not how I did it in first hour. We did it differently. But I'm switching it up because I'm crazy. I'm going to count by pi over 4s. So every chunk of 45 degrees, I'm going to count 1 pi over 4, 2 pi over 4. Ready? 1 pi over 4, 2 pi over 4. So this must be 3 pi over 4. This is 4 pi over 4. I already have that. This next 45 chunk is 5 pi over 4. This last one down here must be 6 pi over 4. Is that the same thing as 3 pi over 2? Okay, cool. 6 pi over 4. One more. 7 pi over 4. And y'all already had the 8 pi over 4 because it already was filled out as 2 pi. Okay. We're getting there. Who you want to do next? But you don't have a calculator, and you only have 10 minutes to fill out the whole unit circle. So I wouldn't suggest that method, but that's a good thought if you were in a jam, yeah. Do you remember what this little guy is? Pi over 6 is the smallest radian fraction you have on the unit circle. Very good. Do you remember what this guy is? Pi over 3. So you have a choice. You can count by pi over 6s, which is every 30 degree mark. Or you could just think really hard. You could count backwards from pi. We got things to fill out. Me personally, I count by pi over 6s. So every large chunk of 30 degrees, I count a 1 pi over 6. Ready? 1 pi over 6. This guy is 2 pi over 6. This guy is 3 pi over 6. This guy is 4 pi over 6. Give me a better name for 4 pi over 6. 2 pi over 3. So the next 30 degree mark is, remember this was 4 pi over 6, so this guy must be 5 pi over 6. Another way to get here is just to back up 1 pi over 6. 6 pi over 6, backed up 1 is 5 pi over 6. Okay, 5 pi over 6, 6 pi over 6, this must be 7 pi over 6. Notice I'm skipping over the 45s. This guy must be 8 pi over 6. Give me a better name for 8 pi over 6. 4 pi over 3, thank you. 8 pi over 6, this is 9 pi over 6. It's already filled out. So this next one is 10 pi over 6. Give me a better name for 10 pi over 6. 5 pi over 3, thank you. This is 10 pi over 6. This next one must be 11 pi over 6. And this must be 12 pi over 6. Nailed it. All right, so that's why I chose to fill out the 45s first, because then I knew to skip over them when I was counting by pi's over 6s. That's how I do it. Like, if someone gave me a quiz right now, it's exactly how I would do it. I try to teach it in a way that's helpful for kids. I don't know if that part's helpful for you. That's just the way my dyslexic brain has to roll. Some kids have decided, Abruzzo, I'm just going to need to memorize these fractions because it's not going to work. And I said, okay. Then if that's your case, you might want to just hurry up and write down the radian measure as soon as you get your test. Okay, the next part, that was actually, in my opinion, the hardest part of the unit circle, but that's me. I'm going to fill out what are called the quadrancials, which are these axes. And these are really obvious ordered pairs if you think of this like a coordinate plane. Remember the ordered pair here? 1, 0. It is cosine sine, yes. But if you think of it as being a unit circle of radius 1, then it's like 1 over 1 up nothing. So this ordered pair here is 0, 1. This guy over here is -1, 0, thank you. And this guy down here is 0, -1, thank you. Okay. And this is where I break out the colors. Okay, we got 3 families. You've got the 30, the 45, and the 60. And we're going to fill out the first quadrant, because I know if I mess this part up, I'm going to be in trouble. Somehow you have to memorize which ordered pair goes in the first ordered pair here. Is it the square root of 3 over 2 for the cosine, or is it the 1/2 for the cosine first? And there's some weird trick with your hand, and I don't know what it is. I've never learned this, and I know Osar taught it to you, so if you can teach it to your friend, go ahead. You guys did learn it. I just don't know what it is. And you know what? If you go to YouTube, if you go to YouTube and you look up like developing the unit circle, like I went to go find my own video There was like 4,000 videos before my video that, like, I even wrote Abruzzo Math, and there still were 4,000 videos before my video. Like, every day someone posts a developing the unit circle video. So, if you don't like how we've done it, go look up your own video. All right, square root of 3 over 2, comma 1/2. Cool. I'm going to switch to a new color now. Do you remember the ordered pair from my favorite family, the 45s? It's the easy one, yes. Square root of 2 over 2. And square root of 2 over 2. I know you meant that. And then the 60 is a whole lot like the 30, but reversed. So that's a 1/2. And then square root of 3 over 2. Okay. I'm feeling good, because everything after this is easy peasy lemon squeezy. I'm going to run out of room, because I got, like, not a lot of room to write, but you should be writing out of the top 3 trig functions. You don't have to do all 6, just the top 3. Who's positive and who's negative in each quadrant. So who's positive in this first quadrant? All of them, yeah. The mnemonic device is all students take calculus. But all of them are positive in this first quadrant, so you'd have to write sine, cosine, tangent, or some abbreviation of those. Nothing's negative in the first quadrant, right? And notice in your first quadrant, yeah, true. All right, I'm going to start with the blue family, because I got a blue pen open right now. This guy right here. Who's his cousin over in this quadrant? 150, yeah, this guy. So this ordered pair is going to look a whole lot like this ordered pair, except tell me the one thing that's different. The sign on the cosine, the first quadrant coordinate, is negative. Now, guys, this should make sense to your brain, because if you think about this as traveling left and then up, yeah, that ordered pair would be negative comma positive. All right, who's the cousin down in quadrant 3? This guy. Now this time, both coordinates are going to be negative. So you have negative square root of 3 over 2 and negative 1/2. And then his cousin over yonder, whoop, is this guy, which is positive square root of 3 over 2, but the negative 1/2. So notice the visual symmetry there, guys. They all have the same reference angle. We'll learn about that again tomorrow. But they all have the same reference angle. They're all cousins. Just got to watch your signs. All right, let's talk about the green family. That's not green. Try again. Green family. This guy. So his cousin over here, oh man, is square root of 2 over 2, comma square root of 2 over 2. However, I need this first coordinate to be negative. All right, his cousin down here, both of them are negative. And then his cousin down here, oh man, the sign value, excuse me, is negative. So square root of 2 over 2, comma, negative square root of 2 over 2. All right, almost home free, guys. 3 more things to fill out. We got this. Red family. Oh, for Pete's sake. All right, his cousin over, oh man. His cousin over here is negative 1/2 square root of 3 over 2. Cousin down here, oh man, is negative, negative. Yeesh, cousin right there is positive 1/2 negative square root of 3 over 2. And we're all filled out. I didn't catch our time, I wasn't watching the clock, but pretty sure we're still within our 10-minute range for that part of the video. And plus, I blabbed a lot during it, so you'll be fine. I like the colors. I think they help, and I think they help you catch mistakes. The other thing I would do, because, you know, it's not time yet, I don't have to turn my test in yet, I would go through and watch all my signs. And I would look, okay, in this quadrant, are all my, quote, x values or cosine values, are they all negative? Yep, yep, good, good. All the y's or signs positive? Yep, yep, good. Both things should be negative in this quadrant. And then in this quadrant, the sign or the y values, if you want to think of them that way, should be negative. So, me personally, I think developing the radian measure is the worst part. I think common mistakes occur where like signs get left off because you guys are so excited to fill them in that you lose a negative when you needed one. So just before you throw the test at me, if you still have time, stop and watch your negatives and look for them. Okay? And yeah, if you have loads of time for some reason and you're thinking, oh, I think I might have messed up on this 1 radian measure, yeah, by hand you can calculate, you can convert a degree to radian. I don't think you're going to have time to do that for many of them, though. So I don't want you to approach the test with that method in mind. But if you have extra time at the end, then there's that. All right.